Back to my YouTube channel. My name is Lokesh Koda. I am the student of Sri Venkateswara College of Engineering. My USN is 1V22IS030 and the subject is Mathematics. Topic Markov Chain. Description. Sometimes we are interested in how a random variable changes over time. The study of how a random variable evolves over time includes stochastic process. An explanation of stochastic process, in particular type of stochastic process known as Markov chain, is included. We begin by defining the concept of a stochastic process. What is Markov chain? One special type of discrete time is called a Markov chain. Definition. A discrete time stochastic process is a Markov chain if for t equals to 0, 1, 2 and so on all states p of x t plus 1 equals to I x t plus 1 mod of x t equals to I L x minus 1. Essentially, this says that the probability distribution of the state of time t plus 1 depends on the state of at time t of I L and does not depend on the state the chain passed through on the way to I of the at time t. In our study of Markov chains, we make further assumption that of all states I and j and all t p xi plus 1 is independent of t. This assumption allows us to write p of xt plus 1 equals to j, xt equals to I, pij, where pij is the probability that given the system is in state I at time t will be there in a state j at time t plus 1. If the system moves from state I during one period to state j during the next period, we call that a transition from I to j has occurred. The Pij's are often referred to as transition probabilities of the Markov chain. This equation implies that the probability law relating the next period states to the current state does not change over time. If it is often called stationary assumption, and any Markov chain that satisfies it is called a stationary Markov chain. We also must define Qi to be probability that the chain is in state I at the time 0. In other words, Px not equals to I equals to Qy. We call the vector Q, Q1, Q2, so on Qs the initial probability distribution for the Markov chain. In most applications, the transition probabilities are displayed as X S into S transition probability matrix P. The transition probability matrix P may be written as shown in the figure. For each I, summation of I j equals to S summation j equals to 1, Pij equals to 1. We also know that each entry in the P matrix must be non-negative. Hence, all entries in the transition probability matrix are non-negative and the entires in each row must sum to 1. Example problem. Suppose Max and Patty decide to flip pennies. The one coming closest to the wall wins. Patty, being the better player, has a probability 0.6 of winning of each flip. In Patty starts with 5 pennies and Max with 10. Then what is the probability that Patty will win? Wipe Max out. What if Patty starts with the 10 and Max with 20? Solution. The desired probability is obtained from equation and 1 3 by letting I equals to 5, n equals to 15 and p equals to 0.6, and the desired probability is 1 minus 1 0.98. For application of gambler's ruin problem to drug testing, suppose the two new drugs has been developed for treating a certain disease. During drug I as cure rate I equals to 1 comma 2 in the sense that each patient treated with drug I will be cured with probability p high. These cure rates are however not known, and suppose we are interested in a method for deciding whether p1 then p2 or p2 then p1 to decide upon one of these alternatives. Consider the following test. Pairs of patients are treated sequentially with one member of the pair receiving drug 1 and other drug 2. The results for each pair are determined and the testing stops when the cumulative number of cures using one of the drugs exceeds the cumulative number of cures when used the other by some fixed predicted number, more formally let xj10 if the patient in the jet pair to receive drug number 1 is cured, otherwise 1 if the yj 1 if the patient in the jet pair to receive drug 2 is cured, otherwise. For predetermined positive integer m, the test stops after pain n, where n is the first value of n such that either x1 plus so on plus xn minus y1 plus so on plus yn is equals to m, or x1 plus so on plus xn minus y1 plus so on yn equals to minus m. In the former case, we then assert that P1 is at P2, and in the latter, then P2 then P1. In order to help ascertain whether the predicting preceding is a good test, one thing we would like to know is the probability of it leading to an incorrect decision. That is, for given P1 and P2 where P1 is P2, what is probability that the test will incorrectly assert that P1. To determine the probability, note that after each pair is checked, the cumulative difference of cures using drug 1 versus drug 2 will either go up by one probability P1 1 minus P2, since this is the probability that drug 1 leads to cure and drug 2 does not, or go down by one probability 1 or remain the same with probability P1 P2 plus 1 minus P1 1 minus P2. Hence, if we only consider those pairs in which the cumulative difference occurs, then the probability will go up with probability 1. P equals to P up 1 or down. P1 of 1 minus P2 divided by P1 1 minus P2 plus 1 minus P1 of P2, and down 1 with probability Q is equals to 1 minus P equals to P2 of 1 minus P1 all divided by P1 of 1 minus P2 plus 1 minus P1 of P2. Hence, the probability that the test will assert that P2 in P1 is equal to the probability that a gambler who wins each bet, the probability P will go down m before going up m. But equation 4.12 that I equals to m n equals to 2m shows that probability is given by P test assert that P2 and P1 1 minus 1 minus of 1 minus q divided by p whole to the power of m whole divided by 1 minus q divided by p whole to the power of 2m equals to 1 by 1 plus p divided by q to the power of m. Thus, for instance, if P1 is equal to 0.6 and P2 is equal to 0.4, then the probability of an incorrect decision is 0.017. When m equals to 5 and reduces to 0.003 when m is equals to 10. Thank you friends. Please share and subscribe my channel.